And thank you everybody for joining us today for our C2 Smart webinar. I'm Lizzie, a research project manager at C2 Smart, which is a US DOT Tier 1 University Transportation Research Center. And C2 Smart leverages recent advances in big data and technology to solve today's urban mobility challenges. Today's webinar is exploring cost-effective computer vision solutions for smart transportation systems, urban work zone detection, and safety analysis using near-miss data. Our presenter is Dr. Jenny Yao. She is a dedicated professional with a passion for transportation and over 10 years of experience in the field. As the Assistant Director of Research at C2 Smart, she has focused on emerging technologies and urban analytics for smart transportation. She is best known for her research on evaluating the field performance of connected vehicle safety applications, AI-based transportation solutions for smart cities, assessing the mobility and policy impacts on transportation systems during COVID-19, and double parking analysis. And this year, Dr. Gao was named as a Who's Who of Professional Women and is a recipient of the Dr. Louis J. Pignataro Memorial Transportation Education Award by the ITE-MET section and National Leadership Legacy Award from the WTS GNY chapter. And we are also joined by Dr. Xiaoan Chu, a postdoctoral associate at C2 Smart and an associate professor at the School of Transportation and Logistics at Southwest Jiaotong University. His research interests include traffic safety on urban roads and freeways, connected and autonomous vehicles, and emerging transportation data analysis. He has published more than 20 papers in various journals and conferences, and also has research contributions to projects funded by NJDOT and the FHWA. And as always, we will be recording this presentation and then uploading it to the C2 Smart YouTube channel. And we encourage everybody to ask questions today by pressing the Q&A button at the bottom of the Zoom window, and then we'll read out your questions at the end of the presentation. And with that, I will hand things over to our presenters to get us started.
Thank you, Lizzie. And let me share my screen.
Perfect.
See the screen? Okay, perfect. Yep. All right, good afternoon, everyone. I'm Jenny Gao, and as Lizzie introduced, I also have Dr. Chuan Xu with me today. We will be presenting our research on exploring cost-effective computer vision solutions for smart transportation systems. And we will be mainly focused on two sub-applications today. One is for detecting urban work zones, and another one is more or less about safety analysis and visualization using near-misses data. So just a very brief introduction of our team. This is a research project that co-led by me and our center director, Dr. Karnatway, and we have a mix of graduate and undergraduate researchers at NYU to help us develop the two applications. And we also have an industry partner, Mark Davis, who is formerly a mobile eye data service lead that provide us a sample data from the industry of the near misses information they collected from their fleet vehicles. And just to start with, I'm pretty sure everyone is very familiar with computer vision already. So I'm going to just talk in one sentence about how computer vision actually what it's doing is try to turn existing infrastructures, for example, the traffic cameras, into smart sensors in various ways. And I would say, every day there are new applications being continuously developed. And some of the recent use cases in transportation include vehicle counting, pedestrian counting, cyclist counting, and of course, like incident detection, or illegal parking detection, lane usage, curb monitoring. And here are some examples. Everything on the left are developed by our C2 Smart research team, using fixed sensors, basically the CCTV cameras that are publicly available throughout the city. And as you can see from the animations, these use applications ranges from the commonly seen, vehicle counting, speed estimation, current monitoring, to a little bit more complex, like what we did during COVID for social distancing, or like pedestrian posture prediction that can be used for connected and automated vehicle. applications. And on the right is an animation from our industry partner Mobileye. This is using their in-vehicle camera installed on the windshield to sense the driving sense. And I believe this is a road test in New York City. They'll be able to see the segmentation of the roads and detection of the moving vehicles in real time. So the research goal of this project is really to try to demonstrate the feasibility and how cost-effective these computer vision technology can help us in generating not only the mobility data, but also the safety data to provide support for either planning or operational purpose. And we basically developed two sub-applications. One, as I mentioned, one is for detecting urban work zones. And the second is try to do a safety view map application that, including the visualization of a safety scoring system that be able to show us where are the hotspot of safety risks. And the key difference, I would say, in this research project with all of the other computer vision research are, first, we want to focus on a complex urban environment. So everything is built and customized for cities like in New York City, where we know that there are a lot of mix of pedestrian volume, vehicle movement, activity on the curb, and high risk for certain locations. And we also want to prototype these applications for real-world implementation, so they can be used in real time, in simply built like web-based application tools so that it can be simply used by users who are not familiar with the technology. So that's kind of the two primary goals that we have for this research. And how it works. Let me start with the general, I would say, data acquisition framework that we developed for this research. There's basically two video and image input sources. One is from the fixed cameras, and let's take New York City as an example. So we extract information from those 900 public available CCTV traffic camera that are operated by New York City Department of Transportation, DOT. And the second source is we have the near-miss data or information that are extracted from the in-vehicle cameras provided by our industry partner. And then we sample these information, we store the data, the raw data on our server, and we develop the object detection and machine learning algorithms, plus some post-processing filters that customize for urban environments. And then we have a modular for data analytics and data decision support system to be able to show us, the performance measures and solutions that might be provided by these data. And finally, we embedded everything into a web-based application that has different services of different applications. And the advantage of this framework is, first of all, it enables this real-time detection. And second, for the CCTV camera approach, it builds on existing resources, so there's no new cameras are needed for that approach. And for the in-vehicle camera from the crowdsourced, connected vehicles, that approach kind of offers some new performance measure and safety risk indicator for decision maker. And finally, the last advantage, I would say that this framework is very adaptable to other cities and states. And to actually validate, if this approach is really scalable and can be generalized to other cities or states, we did a small review on, how many public available camera systems are in the US. And we come up with this resource sheet from more than 50 cities and states in the US. And this just giving you an example of what information that we actually look for. That include, the number of cameras for these cities or states, the spatial coverage, whether it is providing a continuous streaming, like videos, or sometimes it can be discontinued images, the resolution of the camera, and also if those cameras are facing highway or urban streets. And on the right, these are the graph and figures that showing you the distribution of these camera system and the scale of each of the camera systems. So basically, we can tell that, almost more than half of these camera systems in the US are with a scale of 100 to 1,000 cameras. And these are all existing sources, which means, if it worked for New York City, highly possibly this approach can be adapted easily to all of these other camera systems among different cities and states in the US. And one last key point before I dive into the detailed application, this research uses a very collaborative approach. So instead of the traditional system V engineering approach, I'm pretty sure everyone knows about that. We use more towards agile management approach that, we come up with an advisory board and we ask these advisory board members, they're coming from different agencies, to provide us a wish list of application and desired features. And then we say, you know what, C2 Smart and our industry partner, we can offer fresh perspective and problem solving strategies. And then we obtain periodic feedback from the advisory board members. And finally, we develop these practical tools for the city. And for step 2 to 4, there's a feedback loop over there. So, every few months, we meet together with our advisory board members and to either tailored our direction or desired features based on the unmet demand from the agency members. And we actually, for this project, we successfully assembled an advisory board with 11 members from 5 different local agencies. And I actually would like to thank the report from NYC DDC, especially the Tongue and Gum program, City DOT, OTI, Office of Technology Innovation, Department of City Planning, as well as Port Authority in New Jersey, New York and New Jersey. Okay, so our first application, we name it WorkZoneX, WorkZone Explorer. And the goal is really to detect work zones in an urban setting. There are a lot of change here for this particular research question because, first of all, not like pedestrian or vehicle detection, which we know the computer vision for detecting these type of objects are pretty mature. For work zone, there is currently no public available training image data set for work zone on the roadway for this type of detection. And most of the existing study focus on either the off-street work zones, mostly are the work zone site for buildings, or a single type of work zone object, for example, only the detection for traffic cones. However, and we know that there are some commercial tools that are able to detect like cones on the highway, but I think like none of them are specifically built for the urban environment. But if you're living in an urban city like New York City or any other city like BC or Chicago, you possibly will notice that these urban work zones are very different from the highway work zones, because highway work zones, they have pretty standardized form, right, of work zone. You have road worker ahead signs, you have traffic cones. But for urban work zones, sometimes it can be as simple as a steaming van on the street, which is annoying, but it is a work zone. And it's creating roadblocks, for the cars to pass around, and may create some safety risk on the street. And the other key challenge over here, which is mentioned by many agency members, are the detection of work zone related object, which means, for example, a detection of a traffic cone alone. It does not really mean this is a true work zone, because sometimes it can be very random. It can be people just randomly put a traffic cone behind their car. It can be a set of barrels in a parking lot, but that does not mean it is a work zone. And so that's a key problem that has not been addressed by anyone else yet. But at the same time, we also have some opportunities because our center started to collect those image data since the outbreak of COVID. And that's been 2 years, 3 years of we collecting these images for New York City, and these data sets may contain many urban work zones from the real world. So based on all these implications, we developed this 3 modular framework, and the first module we call it data-centric training. I'm going to details later on in a few slides, but this part is mainly try to improve the training data set for work zone detection. And then we also have a second module called Topology based Inference. This is try to address the problem that I mentioned, a single work zone or some combination of work zone object does not mean a true work zone. So this one, the topology based scoring, we will be looking into the placement of these objects and how many of them in, from the image. And then we build a classifier to determine if it is a true work zone or not. And the third modular, this is coming actually from one of the agency member that's from DDC, I believe, and he said, one question that DDC is very interested in is, what is the size of the work zone? How many lanes it is blocking? So based on that feedback, we developed this reference-free size estimation to help us to estimate the width and length of a work zone that detected by the camera. So going a little bit in more detail of each of these modular, for the data-centric approach, so most of the existing AI applications are actually using model-centric approach. And you might not be familiar with the term, but I'm pretty sure most of you are familiar with how it works. So basically, data collection is treated as a one-time event. We only do data collection once. We only train our model once. And the other efforts are more focused on how to improve the model architecture, how to fine-tuning the hyperparameters inside the AI model to enhance the performance. However, the problem for this particular work zone detection is that the current limitation is really the lack of data rather than the shortcoming in the models. That's why instead of just using a model-centric approach, it is better to use a data-centric training approach that will systematically augment training data sets with the goal of enhancing the model accuracy. And basically what we did is we first identify 11 work zone related objects, and some of the category are more related to like urban work zone, like vents, like manhole guardrail, like trench covers, and some of the others are more common and same work zone type, like traffic cones, barrels, fences, work zone signs, construction vehicles, and workers. And second, we compose a mix of training data set from different sources. So our main data set is still the CCTV cameras because we have 2 years of data of these real world images. But what we notice is the gap is for some subcategories, we don't have good detection accuracy. However, detection accuracy is very important for the model. For example, construction workers or construction vehicles. So be able to fill in that gap, what we did is we supplement a second source. These are the web mining images from Freestock, image website. And they have very high resolution images, and they have actually good amount of image on particular subcategories such as workers or construction vehicles. And thirdly, we also supplement another source of data, which are from a 3D simulator. So we built some synthetic image or work zone images from a 3D simulator. And the purpose of having this data source is as long as we have the 3D model of different work zone equipment, we are able to place as complex as possible the form of the work zones, and we can see like 360 degree of the work zone from different angles. So it will help us to augment work zone site images from different angles, from different kind of setting. And just to remember, the goal here is really to use the second and third data set to supplement the subcategory that we do not have a very good detection accuracy. And I'm not going to the detailed mathematics here, but just to highlight, besides supplementing different data sources, this improvement process is really an iterative, improvement process. So we did it a couple of times, and we also do a data cleaning, pruning and fixing some of the labels to have a cleaner training data for the detection model. And the second modular, we name it topology-based scene inference. And over here, the key is really to look at to understand the positional relationship and the connections among detected work zone objects. Just giving an example, it could be several cones placed adjacent to a line of fences. So this topology complexity score will give us some indication of I would say the form or the setting of the work zone. And if we combine these information together with some other input, for example, the number of work zone objects per type. Let's say if I have a work zone have 10 cones, 2 fences, and the setting of that detected objects is something like a closed loop like this, then maybe highly possibly this will be a true work zone. But instead, if we only detect 2 cones and they're randomly placed at different corners of an image, then very less likely this will be a true work zone. So we input all these information into a machine learning classifier, and here we use actually Boost classifier. And it is a supervised classifier that we train on some ground truth WorkZone sync data from the CCTV cameras to help us to determine, whether or not this is a true WorkZone based on these positional relationship and the number and types of the WorkZone object detected. And the third modular is for size estimation. And the key here is we call it reference free. This is a method that we actually adopted from one of the previous research that we did for social distancing for a pedestrian pair. And the key here is instead of going to the field and to use a reference to measure the distance, we assume some standardized height of common WorkZone equipment and try to establish a scale. This is because most of the traffic cones, they are within certain height. And maybe like for barrels, same thing, they have certain or very similar height of all those barrels and barrels. And basically, based on that, we divide the images into several hyperplanes, and each hyperplane exhibits a unique row to pixel distance rate, we call RP rate, as the number of pixels corresponding to a real world length varies between hyperplanes. So basically, if we know the standard height of a traffic cone, we know how many pixels it occupies in an image, we will be able to develop, this scale or this RP rate. And that will help us to estimate the size of the WorkZone. And then we separate all these approaches into 4 different models for comparison. And of course, we have a baseline model that is using only the CCTV images as training, but there's no data-centric training. It's used very normal model-centric training. And then we have a model B that is using CCTV images plus data-centric training. Model C, CCTV images plus free stock images plus data-centric training. And model B is basically having all 3 data sources, CCTV, free stock, and 3D synthetic image plus data-centric training. We use 2 performance measures. One is the precision recall curve, as you can see from the upper of the slides, and also the mean average precision, which is MAP over IOU 0.0, which the result is presenting is in this table. So from the figures and the tables, what we can see is, compared to the baseline model, which is model A over here, we saw a substantial improvement after implementing this data-centric training. So we see this, huge improvement in all 3 models. And by supplementing those additional data sources, like, the free stock images, the 3D synthetic images, we are able to increase our model performance to especially some subclasses, including the barricade, the construction vehicles, the WorkZone signs, and chain fence. And some of those subclasses are very important for WorkZone sync identification, especially like construction workers or construction vehicles, because the presence of construction vehicles is highly possible, like indicating this is a true WorkZone. So just giving some visual example of how it looks like. This is during the daytime, and we did calculate the overall accuracy of all time period, the accuracy of WorkZone identification. Sync identification is around 98%, but of course, looking at just the accuracy doesn't mean anything. So we also look at the F1 score, which is a balanced set of precision recall, and we got 0.71, which is, I think, like pretty acceptable and decent, consider the low resolution of the images that we're getting from the CCTV cameras. And this is daytime, but you can see that it also works with pretty blurred cameras, and it is able to detect some of the workers and construction vehicles. These are nighttime examples, and it kind of proved that the model also works during nighttime because our training data set is 24/7. So we do have some good input of both daytime and nighttime. And it is able to detect those, like even the chain fence that might be a little bit hard to detect, consider the low resolution again. And for the WorkZone size estimation, so this one's a little bit tricky just because so the accuracy over here is a random selection of 10 WorkZones that we picked, and we compare with the actual size and the estimated size from the algorithm. But one challenge that we noticed during this comparison is sometimes, the work zones, it might not be using all the cones or barrel to kind of like having a closed loop form of the work zone, because sometimes we use some natural boundary like a curb or a wall as a part of this closed loop. So in those circumstances, it might be a little bit challenged to estimate, a high accuracy work zone size estimation. So we're still trying to dig more into those scenarios. But if it's, in the middle of the road, it has a closed loop by these work zone detected objects, the accuracy of size estimation can achieve with a range of 70% to 90%. And so finally, we have all the algorithm developed. We embedded everything into a web-based tool. And this is just a snapshot of how the map application looks like. And besides the camera with the work zone detected, we also add a particular visualization for a camera that detects a worker, because this is all the detections in real time. So if we detect a worker in real time, that means this work zone is active. So give some indication of active work zone through the map application. And we also combine this work zone detection with some other traffic detection that we developed in the past. So we are able to tell, surround this work zones, what is the traffic condition, how many cars, buses, trucks, pedestrian cyclists that we detected at the same time of the same image surround this work zone. So give us a little bit more information about if it is congested condition surround the work zone at this particular timestamp. And we also have a vote feature, like how you use ChatGPT. If this is a true work zone, we can vote saying that yes, this is true from the web application. And just one last slide before I go into the demo about this web-based tool. Because we have different services, different sub applications into the web-based tool, so we ended up using a microservice architecture of this web application, which is very scalable and extendable. And we adopt many optimization methods, include parallel computing, list virtualization, index catching, multi-thread detection, to lower, the rendering, query, and detection latency, because there are multiple algorithms running in the back, and we were able to actually speed up a lot by using all these combination of optimization methods for the web-based tool. And here is a small demo of the web-based application. This is actually an old video that does not have the latest functionality. But I think it's a just simple demo to show how the web application looks like. This one does not have the worker yet, but we already embedded that function right now. And this is actually linked to all the 900 cameras in New York City. But we are able to filter it by different boroughs, so that if you have a forecast area of Manhattan, it's easier to just see that particular borough. And we can also filter by type. Saying that, I don't care about all of the other camera location. I only want to look at where the work zone are detected. We can filter by work zone, and it will provide a list of detected work zones on the right panel. And if you click on learn more, we'll see enlarged image, and you can actually maximize it to see the detail of the detection output. And then if you click on locate, it will locate back to the map of where this work zone is happening and the original images. We also have a dashboard that's giving some statistics of the work zone at different borough and at network level. Actually, let me quickly go to the latest version of the dashboard, so we'll be able to see. So this is the latest version of the dashboard that, we have count of work zones in each borough. And here it's showing you the duration of each detected work zones. And this red one also showing you some information about how many hours this work zone are actually active. So the red bar is the time duration when we detect a worker in that work zone. We also have short-term work zone and long-term work zone. I think we define if it's over a day, we think this is a long-term work zone. Then we have the last 4-hour work zone count through the city and durations, at the network level. Everything is downloadable, so we'll be able to see like historical information and for these work zone duration and work zone count. And this is trying to provide some methods later on, for further data analysis. And as I said, for the work zone application, we are able to visualize these work zones. Let me show this one. So instead of just enlarge and move around, see the detection outputs, we also have the traffic detection that is showing here at the same time. And we can bold it because this is a true work zone that's identified by the work zone application. And going back to our presentation. So that's pretty much everything about the urban work zone detection application that we developed. And the second application is called Safety View Map. We call it SAFExMAP. And the research objective of this application is pretty different than the work zone one. So basically, we have a sample of near misses data provided by our industry partner, through their ADAS system. But it remains kind of unclear, even till now, that is there a correlation between these near misses events and crashes in real world setting, and especially is there a spatial correlation between these two? And the goal is really to see that if crash data is not available, will we be able to use near miss data as an approximation of crash risk to help us understand maybe some short-term intervention effect that we don't have enough crash data to do an analysis. So based on this challenge, we come up with a data fusion-based approach, saying that what about just integrating multiple safety-related information? We have near misses data, we have historical crash, and we have social demographic information, we have traffic information. Can we develop a safety risk indicator for city street based on all these data that we have? So try to answer this question. We come up with a study area. This is Manhattan, and this is the area that we have half year, 6 months of data of near misses from our industry partner. And this kind of includes about 60K near miss events identified by their fleet vehicles. And it is, last year in 2022, so everything is pretty new. We decided to use a gray cell as analysis unit. So we have kind of like a uniform area, analysis area. And we collect different type of data besides near misses. We also have crash record from NYPD, we have traffic exposures, we have roadways features like road lengths, we have number of transportation facility per grid cell, like how many bus stops, how many subway stations, and we also have land use information. And I'm pretty sure everyone is very familiar with all of the other data sets, so I'm going to skip them, but I'm going to tell a little bit more about the near misses data that we received. So this particular sample data of near miss from our industry partner Mobileye are generated from their collision warning events that were reported by their fleet vehicle with Mobileye ADAS system, advanced driver assistance system. And this collision warning system is based on the estimated TTC, time to collision, which is a very well-known and common safety surrogate safety measure that is a function of velocity and distance. And there are basically 3 types of collisions. One is the forward collision warning, between vehicle and vehicle. Pedestrian collision warning, this is between vehicle and pets. And bicyclist collision warning, this is between vehicle and cyclist. And there are 2 types of fleets. And one is called ME8. These are the fleet vehicles with Mobileye 8 Connect ME8 technology. And all the warnings that generate by the fleet vehicle that installed with the ME8 technology are collected. And the second set of vehicle is consumer vehicles with OEM, with original equipment manufacturing, mobile technology. And for OEM, the sampling collection methodology is pretty different. So we actually only have a subset of the collision warnings. that use with a default collection rate of 1 driver per road segment per hour. And this is how the data actually looks like, you know, on the map. And as you can see, ME8 has a lot of data points, while OEM has much less. But OEM, you know, by the definition of how the data is collected, might be more normalized compared to ME8. And here's the summary of all the potential input variables that initially we come up with, saying that, you know, they might be useful for the analysis. We have crash count, we have crash count for fatal injuries, near misses for the 2 different type of vehicles, number of intersections, subway station, bus stop, road length, VMT, whether it is a highway or not, and all the land use information of, you know, the percentage of residential area, percentage of commercial area, and population. And then here is the key that, you know, we want to understand, is there a correlation between them, right? So we first come up with a correlation matrix of all these input variables, and we found, yes, there is a high correlation coefficient between crashes and near misses, and for both ME8 and OEM. But then that leads to the second question of our research, you know, yes, we found some correlation, but is there a spatial correlation? So we apply a global Morris eye test to examine first, you know, the entire data set. And we found that, yes, there is statistically significant spatial correlation between the crash data set and the near miss data set. But then this leads to our third question, is there a local, you know, spatial correlation? Like, this near miss data, is it good for certain locations or maybe not good for certain locations? So we further apply a LISA cluster map method. This LISA basically is a local spatial correlation test that, you know, we tested for between the crashes and near misses. And basically on these 2 figures, where you see those darker blue and darker red, these are either the darker red are the high clusters and the darker blue are low clusters. So basically, high clusters represent hotspot and low cluster represent cold spot. But both of them means cluster, means like high correlation, either high, you know, high correlation between the 2 data sets. So these are the places that we might be more confident of using near misses data to get some insight for crash risk because they have a stable correlation between them. However, there are also some locations, for example, the Upper West Side over here, you see some lighter red and lighter blue dots, and these are the high, low, and low, high clusters. And basically, these means there's a negative correlation between these. And especially, I would say, like for figure A, on the left, the high-low clusters, basically the Upper West Side, may not be some good places. So basically for this particular area, the utilization of this near miss data should be very carefully considered because it may be a little bit misleading, especially for the high-low clusters, because in figure A, that means we have a high crash count, but a low near miss count at the same location. So this correlation problem needs to be treated, you know, spatially different based on different locations. But again, this is just a sample data set. It can be different for different locations in New York City. And if we have like more data, it might be more comprehensive to understand those relationships. But this first glance on spatial correlation did give us some insight of a better way of using this near miss data. And next, I will hand it over to Dr. Chuan-Xu to talk about how we actually develop this safety risk index.
Okay, thank you. Thank you, Jenny. I'm Chuan-Xu and postdoc associate in SAFExMAP. In this part, I'm going to introduce the safety risk index development and the relevant analysis. We have 6 steps to develop the safety risk index. The keywords are variable selection, ranking, feature importance, sign acquiring, crash frequency incorporating, and add them up. In step 1, we need to decide which variables are used. In the beginning, we apply variable selection based on the correlation matrix, which Jenny mentioned in the previous slides, and the variance inflation factor analysis to avoid multicollinearity. Then the filtered variables are used to build negative binomial models. A step AIC function, which is a function in R package, is applied to find the negative binomial with the lowest AIC. Finally, the significant variables in the optimal negative binomial model are used to develop a safety risk index. In step 2, the row value of the selected variables are converted into rank values. This step is based on that rank values are much more robust to outliers and its independency from distribution assumptions comparable across different variables. Then is step 3. In the literature, most methods that to fuse information from multiple sources use subjective weights. For example, the weights from survey or expert interview. To generate more objective weights, we employ feature importance from XGBoost as a variable weights. Then go to step 4. The feature importance is always positive. However, some variable may have a negative impact on crash risk. Therefore, we adopt the sign of the weight from the optimal negative binomial model. In step 5, inspired by our previous study, we include crash frequency in the safety risk index. This is based on that the historical crash count is still one of the most important and direct indicators to crash risk. In the final step, we multiply each variable's rank score by its weight and add them up to compute the SSRI. Next slide, please. This slide shows a more detailed workflow. We begin from the initial variable pool and then remove variables based on correlation metrics and multicollinearity analysis, then build the negative binomial model with the lowest AIC. From the optimal model, we can extract the sign from the model estimate. Then the XGBoost model was built. The dependent variable is the crash frequency, and the independent variables are those significant variables in the final negative binomial model. After that, we employ the combination of feature importance and sign as weights. In this table, we can see the near miss count ME8 also has the highest feature importance. Next slide, please. After we have all the variable rank values and their weights ready, we can compute the SRI using the above formula. In simple terms, SRI is a weighted sum of rank value of significant variables. Finally, to facilitate comparison and interpretation of the results, we employ a linear scaling technique known as a min-max scaling to standardize the safety risk index within a 0 to 100 range to get the scaled safety risk index, SSRI. Next slide, please. Based on the proposed methodology, we calculated the SSRI in the range of our data set and visualize it on the left side figure. For better visualization, the SSRI values were divided into 10 intervals, with each interval assigned a distinct color. For comparison, crash frequency of each cell is visualized on the right. Crash frequency value per cell only span from 0 to 16, with the 16 being the maximum. This indicates that crash frequency is constrained to integer value within this range. When trying to understand and interpret cells with identical crash counts, and particularly in identifying contributing factors that might need safety intervention, a data fusion approach becomes critical. Furthermore, the data reveals that the majority of the grid cells have a crash frequency within a narrow 0 to 2 range. sole reliance on crash frequency data that limits the granularity of safety risk in representation. Next slide, please. Because crashes are real events, it leads to scenarios where crash data may be limited. Therefore, we also constructed a hypothetical scenario where crash data is unavailable. The left picture is the original SSRI, and the right side picture shows the hypothetical SSRI excluding crash count information. In this hypothetical scenario, the near miss count becomes the highest weighted variable, and the combination of near miss count and other information serves the need to indicate the crash risk. From the figures, we can see that to some extent they are quite similar. Specifically, both of them capture the grades with a high risk surrounding the linkage road and bridges and tunnels, grades along avenues in the middle town. This suggests that even in the absence of crash data, the SSRI can still capture the primary patterns of safety risk within a city. Next slide, please. Moreover, based on severity, crashes can be categorized into property damage only, PDO, injury crash, and fatal crash. However, PDO crashes might be underreported. Therefore, we also constructed injury and fatal crash-related safety risk index that only injury and fatal crash data are used. The results showed for this new safety risk index, near misses count still has the highest weight among other variables. You can see the red circle. From the three figures, it can be observed, although the PDO crashes were removed, the figures have the similar pattern with the previous ones. Specifically, the range of crash frequency is more limited in this situation, only from 0 to 8, and SSRI can provide richer information, safety information than crash frequency. Next slide, please. Finally, we also developed the safety risk index for two kinds of vulnerable road users, VRUs, pedestrians and cyclists, based on the data availability. Because in the mobile data, we have the forward collision warning and also pedestrian collision warning and cyclist collision warning, as Jenny showed in previous slides. Take pedestrian as an example. We filtered pedestrian-involved crash from the historical crash dataset and filtered pedestrian collision warning from Mobileye near-miss dataset. Then follow the same 6 steps to derive pedestrian safety risk index. For cyclist safety index, the procedures is the same. For pedestrian SSRI, the variable weights highlight road length, number of intersections, population, commercial land use rate. For cyclists, the weights highlight road length, population, residential land use rate. A noteworthy observation in our results is the role of VRU near-miss data. Despite their significance and positive associate in crash modeling, their assigned weight is relatively small. You can see that in the above tables. This may be due to the scarcity of near-miss data specifically related to VRUs. It can be addressed by using data from longer period. In the two figures, the SSRI highlights several dispersed high-risk locations for VRUs, which need to be further investigated. Okay, that's all from me. Let me hand it back to Jenny.
Thank you, Chuan. And I think we have maybe 1 minute that I can just quickly show the application. very quick. This is still in a beta mode, but I think it might be interesting to quickly show. So we have like different data visualization. We have different data sources, safety related information, hazard on the road, traffic crashes. This may take a few seconds. Just giving an example of a heat map, 2D heat map of the near misses data, and the final safety risk. We can filter that for only the vulnerable road users or everything. And this is how it looks like on the study area. And for the skills, we kind of separate it into different classes, and the red one are the risky one. And by clicking on 2 different locations, we can also see a simple tableized comparison of that. This application also provides some spatial temporal analysis that allowed us to draw a polygon of places. I don't think I'm going to show the results, but just let you know, it can also do like segment selection or area selection, and showing the spatial temporal analysis of these data if I actually run it. Just going back to the slide to conclude everything for the sake of time. So we established this automatic pipeline for data acquisition, and also built this web-based tool that integrated, different computer vision algorithm, machine learning algorithm for the 2 selected applications. The first one, the WorkZoneX, using all the CCTV cameras in New York City as a demonstration. And we're able to detect WorkZone elements as well as a WorkZone scene identification, and we're able to detect active workers, active work zones, traffic conditions around the work zones with a decent accuracy. The second app, as Chuan described, it provides a risk indicator scoring system with a map interface. So it allowed different overlay of data layers for planners or city agencies, decision makers to play around with different data sets, especially for near misses and crash. And also our safety analysis proves that there's a positive spatial correlation found between the near misses and crashes for the particular study area and time frame that we were looking into. So the ultimate goal of this project really is to facilitate the adoption of computer visions for urban area smart cities, and hopefully, these cost-effective solutions will help positively impacting the planning and operational process in the future. But of course, we have some limitations. Currently the SSRI method is a one-time index using 6 months of data, because we only have 6 months of data for that. In the future, once more data becomes available, we plan to implement it as a time-dependent algorithm. And hopefully, besides near miss and crashes, we will be able to use more dynamic variables like speeding tickets. And for the WorkZoneX, I think a very natural or intuitive integration is to integrate this detection tool with another tool that we developed to estimate the impact of work zone, or like coordination management of work zone, so that we are not able to just say that, hey, these are the work zones that's happening on the road, but also be able to tell the impact of these work zones on the road. And I think for this particular tool, we can refer back to the previous C2 Smart webinar on the device tool that developed by our team as well. And that's it. Thank you, and we're happy to answer any questions.
Great, thanks guys. We currently have 2 questions. And the first one is, will it be possible to get a copy of this presentation at a later date?
Lizzie will be able to answer that question, or I can kick in, but I mean, the recording of the webinar will be provided. I'm not sure if the presentation slides will be provided as a separate, file, but we can do that if needed.
Yeah, we'll record. This is being recorded. The webinar itself will be online, but maybe you can email one of us if you want the slides, if you're comfortable with that, Jenny. The next question is, what is the best way to get involved with this research project as a grad student outside of NYU?
That's a good question. I mean, if you are one of if you're a student of one of the consortium of C2 Smart, Consortium University of C2 Smart, I'm pretty sure there's a mechanism of, how we can collaborate with the professors among different universities under C2 Smart. But if you're not within the consortium, I know there are certain like summer programs that also accept like non-NYU students to NYU research projects. So that might be a way that you can look into.
Great. And then the last one is, could you share the website?
Good question. So we're still in the beta mode of internal testing. Actually, I think as a part of the USDOT project, we will be able to share everything once the project concludes. So at a later date, yes, it will be shared, but we're still doing some final testing and fine tuning of the website right now.
Great. I think that's it for questions. So, oh wait, you know what? I think we just got one more. Are the CCTV images enough to detect near misses between vehicles and construction workers? It's a two-parter. And then what additional sensors can provide granular data about roadway worker safety?
Okay, so for the first question, first of all, for this particular project, we're actually not using CCTV images for detecting near misses for WorkZone. And the reason why is because the public feed of New York City DOT CCTV cameras are actually discontinued, which means it's 1 images per 2 to 7 seconds, at each camera location. And because of that, we were not able to actually track the trajectory of vehicles or workers. So it will be very hard for safety analysis because safety analysis require higher granularity of data. However, there are 2 different approaches. One is the backend feed of that camera, I believe, are actually continuous. I think we're still trying to make this data agreement with City DOT to see if we can get continuous feed. If continuous feed is provided, it is possible to detect near misses between vehicles and workers at the detected WorkZone location. So that's a natural extension of the current research. And second, we can supplement other data, such as what I said from Mobileye industry partner, that they have these in-vehicle cameras that are recording the continuous feed of what's happening in front of the vehicle. But of course, the other challenge of those is the market penetration rate of these fleet vehicles on the city street. So I would say like each of the projects has its pros and cons. But there's possibility of doing that. And we're just looking at New York City as an example right now, but I'm pretty sure there are other cities which might provide continuous streaming videos. So maybe, try a different city with continuous video can be a good test case for that. Hopefully I answered both the questions.
Great, and we have one more, which is regarding the index. The weights of the features are mainly generated by how well they can predict traffic crashes, ?
I can answer this question. For the index, the weights of the variables are mainly get from the XGBoost model, and the model can output the feature importance, and we use that feature importance as the weights. This is we do that because we want to address the subjective weight selection in the previous studies. We want to get a more objective method to decide the weights. So this may be still not strong enough, but actually it's we think it's a good trial for using the objective method to get the weights.
Right. So the short answer is yes. But I mean, just try to summarize what Tuan just said, because most of the past studies that we see are coming from maybe like experts, vision, or some subjective approaches, and I think the same person just asked an additional question related to that. So the index design is getting from the negative binomial model, but the feature importance is getting from XGBoost, which is able to capture nonlinear, correlation of feature importance or non-parametric feature importance from those variables. So it's not just a linear model.
Great. Now I think those are all the questions. So thank you everybody for joining, and to Dr. Gao and Dr. Chu for presenting at today's webinar. And as we said, a recording will be available on the center's YouTube channel, and we're expecting end of week for that to be available. And this webinar was brought to you by C2 Smart and the USDOT's University Transportation Center program. But thank you everybody again, and have a great day.
Thank you, everyone.
Thank you.
Bye.